First, I would like to start from thanking the organizers putting together this great workshop in this beautiful place. So it's a pleasure to talk here. So today I'll indeed talk about the pseudomagnetic and electric field and topological Weyl and Dirac semimetal. So in tradition of this workshop so far, change of topics every talk. This work is done in, mainly at UBC in collaboration with Marcel Franz and his students, Anthony and you. The references for this works are down here. So first of all, let's recall what Weyl and Dirac semimetals are. They were probably first discussed in the context of liquid helium. Helium, in A phase of helium-3, the Fermi surface gets gapped everywhere besides at the nodal points at the poles of this Fermi surface, and there is linear dispersion, of course, near these points. So the Hamiltonian is written here, and these points are called Weyl points. Let's look at them in slightly more details. Let's just rewrite the Hamiltonian I wrote in the previous slide. So then one sees that all the possible Pauli matrices enter this Hamiltonian. So naively, even if you want to try to add a term which gaps out this point, you cannot add any Pauli matrices. You can either shift the position of this Weyl point in energy or in momentum, or you can tilt the dispersion by changing the velocities. Alternative topological way to think about it is to integrate the Berry curvature around the Weyl points and around the Weyl point, and then one gets an integer number, which is defines the chirality of this Weyl point. Finally, if one integrates this Berry curvature over the surface of the Brillouin zone, one should get 0, and that means that the Weyl cones the total sum of the chiralities of Weyl cones over the Brillouin zone should be 0, and then you can't have an isolated single Weyl cone. So here, this is an example of simplest Weyl semimetal with 2 cones. Then there is a third way to think about the Weyl semimetal, and that is to think about a 2D material for fixed kz as a function of kz in the Brillouin zone. Then this 2D material does not have any symmetries, so it's in class A, and it has gap closings as a function of this parameter kz when you go through Weyl point. So these gap closings are topological transitions, and the 2D topological number, so Chern number changes when you go through these Weyl points. Correspondingly, between the projections of the Weyl cones on the surface of these materials, you get H states, so-called Fermi arcs. Right. So there are. So now to thoughts about solid state realizations of this material. So to realize Weyl semimetal in solid state, so you need to break one of the 2 symmetries, time reversal or inversion symmetry, because time reversal connects Weyl nodes at opposite momenta, but the same chirality, and then inversion connects Weyl cones and opposite momenta, but opposite chirality. So if you have both of them, then you necessarily have 2 Weyl cones at the same position with opposite chiralities. Thus, with a small perturbation, you can in principle gap it out. So there are proposals how to do it with either break-in time reversal or inversion symmetry, and it was indeed realized in inversion break-in system tantalum arsenide. So there is So there is ARPES and quite particle interference data on this from Princeton and Weizmann groups. So they saw Fermi arcs, and so one can faintly see here the red dots are the positions of the bulk Weyl nodes in these materials, and then the Fermi arcs are going between them, right here. Right, so, but let's return to the argument which I gave before, that you, when you have both time reversal and inversion symmetry, you can't have Weyl semimetal, that's true, but actually you can, because you have two Weyl cones at the same position with opposite chiralities, but of course if you have additional symmetry, you can forbid these Weyl cones from coupling together. So the systems which have these additional symmetries, which have two overlapping Weyl cones, are called Dirac semimetals, and for example, they can be protected by additional pi rotation symmetry, which in combination with time reversal symmetry, you can connect two Weyl cones located at the same position in brilliant zone, and then they are effectively Kramers pairs and cannot couple to each other. So, and then indeed, it was also observed in Princeton group. This cadmium arsenide material was shown to have bulk gapless spectra. So one of the characteristic features of this Weyl semimetals and Dirac semimetals is so-called chiral anomaly. So this is known from high energy physics. So when you have a gapless Weyl fermion, then and you apply parallel electric and magnetic fields, then you have the phenomenon of chiral anomaly, and you need to regularize it properly, not to have generation of particles. So in condensed matter, it's actually relatively simple to understand from also from the conventional point of view. So when you apply a magnetic field to the Weyl semimetal, then you get kz-dependent Landau levels, and actually in either of the Weyl cones, so this is the dispersion for the simplest Weyl semimetal, you have, and here there were Weyl cones before we applied magnetic field, so in each Weyl cone you have a chiral Landau level having some velocity in that direction. The chirality of the Landau level is connected with the chirality of the Weyl node. So, so in the simplest case, you have two counter-propagating ones, and then if you apply constant electric field, then what you effectively do, you have position-dependent occupation of the two chiralities, two chiral Landau level. And it's, so in the low energy physics, when you only look close to the Weyl node, that would look like you're pumping, you're losing charge in one of the Weyl nodes, and you have an emerging charge in another Weyl node. But yeah, it's very simple to see in this full brilliant zone picture. So the signature of that in this Weyl semimetals is negative magnetic resistance. So with applying more magnetic field, you get more degeneracy of this chiral Landau level, and you have stronger, better conductance through this material. So now this was all standard about this material. So now let's try to get a different type of perturbation of it, not real magnetic field, but pseudo-magnetic field, and let me walk you through how we obtain that. So to do that, we strain the material. So let's just write the Hamiltonian of the simplest Dirac semimetal, cadmium arsenide. It has 2 Dirac points in the brilliant zone, and its Hamiltonian is written in the basis of p and s orbitals, and it has 2 effectively decoupled blocks. Each has 2 Weyl nodes. So the position of Dirac nodes is just determined by when this mk term crosses 0 energy. So now what happens if we try to strain this material or change the position of the atoms in this material? So the simplest type of strain, that is you pull or push on the material from one direction, that changes just the distance between the atoms in this direction, in that direction in this case. This just modifies the Hopkins in that direction in the first order like this. And then there is a more complicated type of strain than when you shear the material. So you move, say, atom on top to the right. Then if before you strain the material, there was no Hopkin element between s and p orbital because of the lobe structure of the p orbital. Now, if you move it to the right, there is an additional term in the Hamiltonian which describes this Hopkin between s and p orbitals. So more formally, this Hopkin in that direction, so it gets modified like this. So you change indeed this. So the Hopkin was between s and p, so you just change this Hopkin, and then you add Hopkins between s and p. This change is written through the symmetrized strain tensor. Right. So, and then to obtain the how this enters the low energy theory, one needs to project this Hopkin Hamiltonian change in the Hopkin Hamiltonian onto the low energy theory. And then actually what one gets is the effective, the term which enters the Hamiltonian as a vector potential. These vector potential elements being the elements of the strain tensor multiplied by the factors dependent on the lattice constant and distance between Weyl points. So again, here we can rotate this system by pi around z around x or y direction, and that changes the sign of strain, but it maps the system to itself. So actually the effective vector potential in the 2 Weyl cones is opposite. So the 2 Weyl cones feel opposite magnetic or electric field. So similarly, now to the real magnetic field, we can write the anomaly equations in this case. So here, let me walk you through this equation. So before we had only first term where the rho 5 and J5 was the difference between the density and current of the electrons in the 2 Weyl cones. So now, as our effective electric and magnetic field don't have to be the same in the 2 Weyl cones, you get all types of terms in this equation. So when you replace either magnetic field or electric field with this pseudoelectric or pseudomagnetic field, which is opposite in the 2 Weyl nodes, then of course the anomaly equation, in anomaly equation, this should mean not opposite generation of particles in the 2 Weyl nodes, but the same. So here you have anomaly equation for the real density and current. And then if you have both pseudoelectric and pseudomagnetic field, you have still contribution to the previous ρ5 and G5 terms. So in the terms of the chiral and tau levels, what does it mean for the bulk? Yeah. No. But no, it's not an issue because so this is not, so basically they act oppositely in the two Weyl cones, so right. So okay, here, so in the simplest case, okay, let's walk through time reversal symmetry. In the simplest case, when I'm looking at two Weyl nodes, we necessarily broke time reversal symmetry to get two Weyl nodes. With time reversal symmetry, you must have 4. If you have 4 of them, then there is another pair of such equations for the time reversal partners of the two the two Weyl cones. Yeah. No. So let me. No. And I'll get to that. So that's where I'm going to. So this is the bulk equation. So yeah, let me answer this question in a couple of in this and next slide. So this. So for the pseudomagnetic field, as we get opposite effective magnetic field for the two Weyl cones, then the chirality of Landau levels is actually the same for the two Weyl cones. So you have chiral Landau levels which propagate in the same direction. So this indeed seems like there is a problem with this, both from the charge conservation point of view and then from the fact that the sum of chiralities in the 1D band structure should be 0. So how is it resolved? It is resolved by looking at the full system here. So the equations I wrote before are for the bulk of the system. So it turns out that for this pseudo-magnetic field, it's important to take into account the edge of the system as well. And importantly, if you have constant pseudomagnetic field applied to your Weyl semimetal, you can't put periodic boundary conditions on the system. So you can't have purely bulk system, you must have an edge. So here is the numeric calculation shown for this for this wire geometry over here. So it's either has a torsion deformation like shown on the left that causes constant pseudomagnetic field throughout the wire, and or real magnetic field is applied to it. Yeah. If I compress this slab. Yeah, current along the surface here. So it connects to the bulk current. So in this geometry, you have, so let's look into this third column over here. So this is the full dispersion, and this is the density of states in the bulk and on the surface. So, yeah. So yes, yes. Yeah, let me give. Yeah. Yeah. So yeah, that's a good question. So so for it depends on the direction of the strain actually, because but because of this projection equation, they strongly depend how this on the direction. So AQ is a small number here. So let me get to this in a second. So in the wire geometry, it requires strong strain, like few percent displacement. Right. So yeah, let's look into this picture a bit more. So we have we are starting from the Weyl dispersion Weyl cones and surface Fermi arcs. Then if we apply a real magnetic field, we get 2 chiral Landau levels in the bulk, but the surface state doesn't change much. Now, if you apply this torsional deformations and you get constant pseudomagnetic field, you have 2 chiral Landau levels in the bulk, which propagates in the same direction, and the surface Fermi arc becomes tilted, and it propagates in the opposite direction as compared to the bulk chiral Landau level. And that is how this question about both charge conservation and chirality of the 1D dispersion is resolved. So you compensate the, so you transfer the charge not between Weyl cones like before, but between Weyl cones and the surface of the material. And then finally, the last column here is to show the equivalence of the pseudo and real magnetic field. So here we apply the same magnitude of pseudo and real magnetic field, and then we see that they exactly cancel each other in one of the Weyl nodes, so you don't have any Landau level coming here. There is only Landau level in the other Weyl node where they add up, not cancel. So we can look in more details into the anomaly equations which come from this pseudomagnetic field. In particular, if we just have electric and pseudomagnetic field, then the master equation will look like the first line here, with a relaxation term added to for us to create a stationary solution. And then we assume some tau scattering time between the counter-propagating states in this system, and this then one gets change of density in the bulk. So there is of course opposite change of density on the surface, so this creates change of current going through the system. So in the limit when we are only one Landau level is occupied, so-called quantum limit in this case, then we get just current due to this pseudomagnetic field and electric field, which looks like in this last line. And then this looks very similar to the usual chiral anomaly expression, except now the relaxation time between the counter-propagating state in the system is not relaxation between spatially in the same position chiral Landau levels, between chiral Landau level in the bulk and surface state. One can actually get that this relaxation time is also proportional to this pseudomagnetic field, because you need to scatter between nearby cyclotron orbits in the bulk, and then the higher magnetic fields, the more scattering events you need to get to the surface of the material. So effectively, this this current going in this due to torsional anomaly is proportional to b squared in this limit when only one Landau level is occupied. In the limit when there are a lot of Landau levels is occupied, then you also have to take into account the redistribution of density between higher levels, so between one chiral Landau level in the band structure and other levels, and then one gets actually b to the cube response of this current. So this summarizes the torsional anomaly prediction for the experimental observation of this. So the more you put torsion to this nanowire, the higher conductance you should obtain, and it goes either b squared or b cubed, depending on your chemical potential. So let's skip this, and it did. We get prediction for the persistent currents in these materials. So we have so if we have simplest case of Weyl semimetal with two Weyl cones, then time reversal symmetry is inherently broken, and then we have persistent currents in the bulk, and then the edge going in the opposite direction. But one can also get the same result for the actual model of cadmium arsenide Dirac semimetal obtained from the first principal calculation. So then one gets in the present. So here you need to explicitly break time reversal symmetry, otherwise you of course won't have any persistent current. Here for same magnitudes of real and pseudomagnetic fields, we get also similar result in that there are persistent current both on the bulk and in the bulk and on the edge of the material. So here the two dispersions are for two spins of the two spin sectors. So right, and here I also come back to your question about the magnitude. So here you for this torsion you need like quite a huge torsion to get sizable magnetic fields. However, we can go around this problem by noticing that this AQ is small for the real cadmium arsenide material, and then we can use the other element of this projection, which turns to be like 57 times more receptive of the strain. So that we just need to use different type of strain, not torsion, but like rather bending of the thin layer of this Dirac semimetal, and we can obtain with reasonable 1% distortion. Or actually 0.5% distortion, I believe, for this case, we can obtain the fields of 1.5 Tesla, say. And the interesting signature in this geometry would be to observe quantum oscillations due to this pseudomagnetic field. So similar to the usual magnetic field, so here's the numerical calculation in this plane geometry. Similar to the usual magnetic field, we obtain Landau levels due to this pseudomagnetic field, and as a function of energy in presence of real magnetic field, you see this nice quantum oscillations. So these black lines, the positions predicted from the continuum model, and the green curve is this numerical simulation. And you see that, okay, at some value of chemical potential, there are deviations between the prediction and the numerical calculation because of the low energy theory does not work too well anymore, and it actually works. The prediction works better for the torsional case. Let me get to why it is like that in a second. So we can also look at the more conventional signature, like density of states or conductance, as a function of applied field or pseudomagnetic field. So here is again numerical calculation for the for this setup where we either apply perpendicular magnetic field or this strain with the on the plane of this Weyl of this Dirac semimetal, and then we indeed have very good agreement between the positions of the peaks in density of states, say, and due to the continuum theory and the strain and magnetic field. However, so let me return to this question why the prediction for the positions of quantum oscillations works due to low energy theory works better for the pseudomagnetic field, and that is because actually two Weyl cones, they feel opposite pseudomagnetic field, so the trajectories due to which we see these quantum oscillations are different for the real and pseudomagnetic field. For the real magnetic field, you have trajectory going around the whole Fermi surface after the Van Hove singularity. For the pseudomagnetic field, the direction of propagation around Fermi surface is opposite, like shown in these red lines here for the two Weyl cones. So you still see half the Fermi surface due to this pseudomagnetic field, and indeed one can see it in different periodicity of quantum oscillations due to strain and magnetic field. Right. So finally, I can briefly mention the other terms in the anomaly. So that is, for example, a pseudoelectric field times magnetic field. So you create pseudoelectric field, say, by time reversal, time-dependent push on the material. So you say apply sound wave to your nanowire made of this material. That would create a time-dependent pseudoelectric field. And in turn, what it will mean is it will cause a redistribution of density between the bulk of the system and the surface of the system. Time-dependent redistribution, and so one can measure either radiation due to this process, which is unfortunately very high. So it's 16-pole radiation in this case, so it has very strong frequency dependence. One can also measure the near field signatures, so just electric field near this material, or one can, that are the main signatures of this pseudoelectric field in this case. With this, let me thank you for your attention.